Hi, in this video we are going to discuss about discrete time Fourier transforms. So what are discrete time Fourier transforms? So my signal x is a discrete time signal xn, and if I multiply it with a sinusoid or a complex sinusoid e to the power minus j omega n with the frequency omega, and I sum over all the time indices or n, then I get x e to the power j omega. Okay, let us take it as a transform, which transforms my time domain signal n into some representation which is a function of omega, the frequency of the sinusoid. Essentially, you can think of it like your xn is any signal, whatever it is, the discrete time one, and your e to the power j omega n is just a sinusoid with a frequency omega, and you are just multiplying with different, when the value of omega changes, the frequency of sinusoid changes, right? um, Now if I want to recover my xn, this is the inverse discrete time Fourier transform. So if I multiply x e to the power j omega with e to the power j omega n and integrate over minus pi to plus pi, I get xn. Okay, so just take it as a formula for now. We will discuss this into details and how it works. You know the logic why it comes, because that if you multiply some signal with sinusoids, you get some useful representation. Okay, this is one way to express. So I can say x e to the power j omega is the Fourier transform of the sequence xn, and equivalently I can say x of n is the inverse Fourier transform of x e to the power j omega. Okay, now let's see if this inverse discrete time Fourier transform actually works. So prove that x e to the power, basically the inverse Fourier transform recovers x of n. It's very simple. Just start with the LHS. So this is simply 1 upon 2 pi integration from minus pi to pi of x e to the power j omega, which is basically summation over n, basically all n, x of n e to the power minus j omega n. Okay, now notice that this n here and this n which we are using as a dummy variable for summation, they are different, right? So it's wise to use m or some other notation to distinguish. Let us use m, right? So okay, and into e to the power j omega n, right, into d omega. Okay, let's see what it is. So this is equal to 1 upon 2 pi integration from minus pi to pi. Let's take the integration in and summation out. X of m e to the power minus j omega m plus j omega n d omega. If I consider only the omega terms, I can take this in, and this one basically I can write summation out. And what is this term now? So this term is basically if m is not equal to n, then this term will be e to the power minus, okay, let's say plus j omega n minus m, and if you integrate it, this becomes divided by n minus m, right? And limits from minus pi to pi. right? So this is equal to, if I put e to the power j omega, basically j pi minus e to the power minus j pi. Now consider, now notice that both n and m are integers, right? So e to the power j pi will be equal to e to the power minus j pi into any integer. So this term will be equal to 0. But if m is equal to n, then this term cancels out. Then the integral becomes simply m minus n is 0. So this thing is 1. Integration of 1 from minus pi to plus pi, which is equal to 2 pi. Right? So considering this integral only here. So this is, then this becomes 1 upon 2 pi summation m equal to minus infinity to plus infinity x of m times 2 pi times delta of m minus n, right? And if you substitute, if you do this integration now, this is simply m is equal to n, so this is equal to x of n, because 2 pi anyways cancels out. So hence, which is equal to RHS. So this is what we wanted to prove. So yes, the inverse Dtft actually works and recovers our xn. Okay, let's look at some examples of Dtft to become familiar with this transform. Let us first consider a very simple signal, which is x of n is delta n, which means my x of n is simply 1 at n equal to 0 and 0 everywhere else, right? So now, what is the Fourier transform, the discrete time Fourier transform of this x of n? Let's compute it. X of e to the power j omega is given by summation xn e to the power n going from minus infinity to plus infinity, right? So this is simply my, now let us substitute the value of xn. So xn is 1 only when n equal to 0. So my xn is delta n, so this becomes only at n equal to 0, so it becomes e to the power minus j omega into 0, which is equal to 1 for all values of omega, right? Now let's go to the next example, a shifted impulse function. So it is shifted in time. Now what will be x e to the power j omega? This will be equal to same thing, delta n minus n naught into e to the power minus which is equal to e to the power minus j, right? So hence we found out the value of e to the power j omega for a shifted delta function as well. Now let's consider another example. What is the Fourier transform of e to the power j omega naught n, which is a pure sinusoid, right? A pure complex sinusoid. So proving this way is a little difficult. So let's go the reverse way, which means I want to prove that the inverse Fourier transform of the right hand side is e to the power j omega naught n, which means x of n is equal to 1 upon 2 pi integration from minus pi to pi x e to the power j omega n d omega. This is the inverse Dtft, right? So let us substitute the value of x e to the power j omega. This is 1 upon 2 pi integration from minus pi to pi. X e to the power j omega is this thing. But if you look at the interval minus pi to plus pi, so k, for k equal to 1, this term won't appear. Okay, it will essentially become 2 pi delta omega minus omega naught plus 2 pi k. Okay, if we assume that omega naught lies between 0 to 2 pi, then this will be appearing only once. Right? So this becomes omega naught. So this 2 pi get cancelled out, and this thing becomes only integration from minus pi to pi. Basically, you substitute your omega with omega naught e to the power j omega naught n. Right? So this is the Fourier transform, the inverse Fourier transform of this thing. So this is so we recover it. Okay. Next is Fourier transform of 1. Basically, if you notice only here that omega naught is equal to 0. And then you recover the whole result. Everything else is same. Okay. Now, next we have Fourier transform of an exponential signal. How does it look like? So this is basically an exponential signal. So this is n, this is x of n. And for n less than 0, it is always 0 because u of n is always 0. For n equal to 0, this becomes alpha to the power 0. So it is 1. And then it becomes alpha square, alpha cube, and it goes on like this. This is when alpha is less than 1. If alpha is less than 1, if alpha is greater than 1, then it will be an increasing sequence. So now let's compute the Fourier transform of this. This is equal to summation of xn e to the power minus j n going from minus infinity to plus infinity. So I will just write n here. So this is alpha to the power n un, which means my n will go from 0 to infinity now, e to the power minus j omega n. So if you notice, this is simply equal to n equal to 0 to infinity alpha e to the power minus j omega whole power n. This is a GP. So sum of a GP, what is the sum of a GP? So it is the first term at n equal to 0, which is 1, upon 1 minus the r, the common ratio. What is the common ratio? It is simply alpha minus j omega. Alpha e to the power minus j omega. But if you remember, the an infinite GP is summable only when the r is less than 1, right? Which means I can say r is alpha. Right? Which means alpha e to the power minus j omega mod should be less than 1. This can be written as alpha mod is less than 1 because e to the power minus j omega mod is 0. This is just an angle on a unit circle, so the magnitude is 1 always for e to the minus j omega. Okay, so hence we proved this. Some insights from these examples. So what all examples did we see? So first we saw a delta function. So it is localized in time, right? Everywhere else. So it is sparse in time. Everywhere else it is 0, only non-zero at one instance. And the corresponding Fourier transform is basically everywhere. So this is localized and this is highly non-localized. Similarly, when you talk about a shifted delta function, it is highly localized in time, and this one has a this one is everywhere. All the frequencies are present, but the phase is this, right? Let's consider another example. So this one is highly non-localized in time, right? It is constant over all the time instants. So, and what we find in the frequency domain, it is highly localized in frequency. And similarly here for e to the power j omega naught n, which is a pure sinusoid, so it is highly non-localized in time. On the other hand, the Fourier transform is highly localized in frequency. So if you remember something like the Heisenberg's uncertainty principle, it is something like that. Basically, the underlying foundation is same, that something which is highly localized in time, it will be highly non-localized in frequency. Something which is highly localized in frequency will be highly non-localized in time. So this is one essential property which we see from our examples. So this was discrete time Fourier transform and introduction. For references, you can consider Oppenheim chapter 2 section 7. Thank you very much.